Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back to this series of lecture on elements of solar energy conversion, and we are looking at the photovoltaic conversion mechanisms, the basics of it. So, today we are here at lecture number 32. Okay. So, for the photovoltaic conversion, what we ended up in the last class with the p-n junction diode. Okay. So, when we bring one p type semiconductor and one n type semiconductor together in close contact, then we have seen the bands will bend as well as it will have a constant Fermi level throughout the junction, across the junction. Okay. And that led us to see what would be the built in potential and why. So, this was the picture we have seen in the last class, right, and this built in potential V naught in the equilibrium potential, which is just obtained because of this close contact of two types of semiconductors. Okay. And we have also quantified that quantity, which is the built in potential, and that depends on the distance between the intrinsic and extrinsic Fermi level in the p type, and same for the n type. Okay. So, here this EI stands for the intrinsic level, or intrinsic Fermi level, and this EF stands for the extrinsic Fermi level. So, we quantified it in terms of, for the first term here is for the p side and second term here is for the n side. Okay. So, let us look at now with individual doping concentration. So, from earlier classes what we have seen that this shift in Fermi level because of doping can be quantified in this fashion. In the n side it will be the natural log of n naught by Ni. N naught is the electron concentration in the equilibrium condition and Ni is the intrinsic electron concentration. Okay. So, you have seen this in the other form, that means n naught we have expressed in terms of Ni into exponential Ef minus Ei divided by kT. So, just now what we have used the log form of that, and similarly for the p type it is kT natural log of p naught over pi. Okay. Okay. Again this p naught stands for the whole concentration under equilibrium for the extrinsic or doped semiconductor, and pi is the intrinsic doped intrinsic concentration of the holes. Okay. So, now in the expression of built in potential, now we can replace these two quantities, the shift in Fermi level with this kT natural log terms. Okay. And this for the p side, okay, plus kT natural log n naught by Ni divide which is at the n side. Okay. So, now we can combine them, bring kT outside, and we can do that P naught in P side multiplied by n naught in n side divided by Pi Ni. Okay. So, Pi Ni we do not have to specify the which side it is, because it is the same base material. Suppose it is silicon and one side is doped with aluminum and the other side is doped with phosphorus. So, that is how we are distinguishing the P side and N side. So, Pi Ni, here I should note that Pi and Ni we do not need to specify side, as both are the same, right. So, intrinsic Pi and Ni, which is the intrinsic value, no doping. So, both sides have the same value. Okay. And this Pi Ni we have seen earlier that it is Ni squared, because Pi is equal to Ni for intrinsic semiconductor. Okay. Now, if we look closely at the extrinsic value, the P naught in the P side, that is what? That depends on the concentration, or that is equal to the concentration of ionized acceptor donor. So, this P naught in P side is nothing but Na, which is the acceptor dopant concentration. Okay. And on the other hand, N naught in N side is nothing but Nd, which is the donor dopant concentration. In the N side you have the donor doping, which is Nd. So, now if we replace these values, we can write Kt over Q natural log of Na Nd. Now, we do not have to specify the side, because Na is always in the P side and Nd is always in the N side. Okay. And the denominator you can write just the Ni squared, because Pi Ni is equal to Ni squared. So, that is again a very important relationship. Okay. Now, one thing I should make note of it, and let me use another color, because this causes confusion in lot of students. So, I should make a specific note of caution that you do not get confused about this thing. So, note that this N naught P naught, okay, equal to Ni squared we have used earlier. Okay. And this is true only for a single material. So, this is true only for a single material. So, if you take either a p doped semiconductor or n doped semiconductor, for them the N naught P naught will be equal to Ni squared. That is what we said, that you can only increase the concentration of one type of charge carrier at the cost of the other, because the product will always be determined by the intrinsic semiconductor concentration or intrinsic carrier concentration squared. Okay. So, here we see N naught P naught is not equal to Ni squared, because the N naught and P naught are not for the same extrinsic semiconductor, right. We have two different materials in N side and P side. Across the junction we have two different materials. Across the junction we have two different materials. So, do not get confused by only the formula N naught P naught equal to Ni squared. That is true only for a single material, and that is why we were insisting upon writing which side we are looking at, P naught in P side, N naught in N side. So, to avoid this confusion, what we need? We need more specific symbol. Okay. A symbol that contains more information rather the information regarding which side we are, regarding the side or type of semiconductor in the or across the junction. Isn't it? So, let us use that formula. Let us say that we use symbol with two subscripts. Okay. So, two subscripted or two subscript symbol. And what does it mean? It means this P is just the concentration of holes, just like before, and this O is also just like before the equilibrium value. Okay. And what we introduce now is this information about side. Which side? P or N? So, in this case it is P side. So, this P naught, it means hole concentration at equilibrium in the P side. Okay. Similarly, we can write P N naught, that means hole concentration at equilibrium in the N side, isn't it? And another example, this is electron concentration at equilibrium in the P side. Okay. So, now we are in a solid ground whether which will not cause any confusion in further analysis. And we should mention that whenever the O is missing, that means it is a non-equilibrium value. It is a non-equilibrium value. Okay. So, P n, this will stand for hole concentration in the N side under non-equilibrium condition. Okay. So, enough about the symbols. So, now what we can write? with this changed symbol. So, P naught is nothing but our acceptor dopant concentration, and similarly N naught is ND, right, dopant donor concentration, and P naught N naught is equal to Ni squared, right. Now, we are talking about a single side. So, that equality with Ni squared holds good, and similarly again if we use the same side, then also the equality will hold good. Okay. So, because let me just say that this in the P side, so equality holds good, and this thing is again in the N side. So, again equality holds good. Okay. Hopefully, now there is no confusion, and we can write this NAND because we need it for the built-in potential expression. So, NAND is equal to P naught N naught. Okay. And what is coming in the denominator of the natural log was Ni squared, which is P naught N naught. So, be careful about distinguishing between the normal symbol and the subscript, okay? Otherwise it may be messy. So, with this modified quantities, what we can write, the built-in potential kT by q is equal to natural log of P naught N naught divided by P naught N naught. Okay. So, now N naught cancels out. So, you have kT q ln P naught by P naught, right. So, you can also write that P naught P naught is nothing but e to the power q v naught by kT. Right. Now, what we have done is the whole concentration in the P side and N side, the ratio we have obtained in terms of the built-in potential. Okay. So, this is the expression of ratio of whole concentration in P side and N side in terms of the built-in potential. Okay, got it? So, what we can write, that under equilibrium the built-in potential determines the ratio of any type of carrier concentration in the majority side and minority side. What do we mean by majority side? Because whole is the majority in the P side and it is minority in the N side. So, that ratio is given in terms of the built-in potential. So, of course, the same equation you can see that you can write it for the electron concentration. So, that means n n naught divided by n p naught will be e to the power q v naught by k t. Okay. Same thing you can write. Now, n is the majority carrier in the n side, or the electron is the majority carrier in the n side, and it is minority in the p side. Okay. And one thing I am not showing, but we can show the width of the space charge region which is also called depletion region, because the charge gets depleted within that particular region. So, it is also called depletion region. So, that can be shown to be x n plus x p, right. Width is the width in the space charge region, width in the n side plus the space charge region width in the p side, and that can be shown to be this. Okay. So, let me just remind you what I mean by space charge region width. So, here you see this is the space charge region width, and it is summation of this x n here and x p here, that is the total width, and x n and x p you can express in terms of this dopant concentrations, and that is how you can write in terms of the built in potential and the dopant concentration. And another quantity that you require is this is called permittivity. Okay, permittivity of the material, and of course, what it means is the amount of charge needed to generate unit electric flux in a medium. So, basically it says that what is the charge that you require to generate unit flux. So, that is the permittivity, and individually you can also write x n is width multiplied by this fraction N A divided by N A plus N D. Okay. Just the simple lever rule kind of expression, and x p will be W into N D by N A plus N D, and you can see that x n plus x p will give you W only. And here we, so N A and N D, they are not necessarily equal, right. So, they are differently doped on the same substrate material, differently doped. Two materials are giving you two intrinsic semiconductors, and you are bringing them together. Okay. So, there is no mandatory thing that N A and N D will be equal. Okay. So, what we can write that the x n and x p, this expression, the dependence on N A and N D is giving you an asymmetric width of the depletion region in the across the junction. So, we can see the depletion region width is asymmetric across the junction. In case N A and N D are equal, a special case, of course, it is possible, they are not mandatorily equal, but it can be equal. So, if they are equal, then x n and x p will be equal and it will be symmetric, but that is a special case, it is not mandatory that they have to be. So, please bring that in mind, and this asymmetry we can write that it extends deeper into the side of less doping. So, this is kind of counterintuitive. Less doping side will be the depletion region width will be deeper. Okay. Now, let us ask these questions to ourselves, like okay, we have seen that across a p-n junction how a space charge region is created, how the distribution will be, and what would be the ratio of this carrier concentration across this junction. Okay. Now, how all of these will affect the scenario, or how will they affect the electron current density, okay, electron or hole current density. Okay. Let us look at that. So, how carriers across the junction will be distributed, okay, and how will they move, right. So, that is the key to the photovoltaic effect. So, we have to understand that, and let me urge you that you please pay close attention to see different things happening together. So, let us first draw the bent bands and the Fermi level. So, under equilibrium, so for now we are still under equilibrium. So, Fermi level will be constant. So, let me draw that first, because that helps in keeping consistency. So, let us have that this is the Fermi level, and let me write that this is the conduction band bent, okay, and what color should I use? This one maybe. Okay. Excuse my bad drawing, but yeah. So, this is the Fermi level which is constant across the junction, okay, and this one is the conduction band and this one is the valence band. Okay. Now, we can see that here in the left hand side we have the Fermi level is close to the valence band, that means this is the p side. So, we can write this is the p side, and on the other hand the Fermi level is far away from the valence band and closer to the conduction band. So, that is n side. Okay. Now, you can see as you have Fermi level closer, so electrons will be more easily available or more in concentration in the n side. So, let us have these electrons which are available in the conduction band more in the n side, okay. And as you go up from the conduction band edge, the concentration of electron will exponentially decrease. So, let us say something of this sort. Okay. So, it is all schematic of course, okay. We are just trying to understand how the things will be affected. And similarly, for the p side we have lot of holes, and again in the valence band, and again the concentration of the same will decrease exponentially as you go away from the valence band. Okay. So, these are holes, and for holes the energy is going up in this direction. So, energy is going up downward for holes. Okay. So, basically as you move away from the valence band edge, right, and these are the electrons in the conduction band. Okay. And you have, so here the energy for these ones, energy for electrons are going up in this direction as you move away from conduction band edge, right. And of course, so these are the majority carriers, electrons in the n side are the majority carriers and holes are majority carriers in the p side. But of course, there will be minority carriers as well, much less in number, but there will be minority carriers. So, what you can say that in the p side you have few minority electrons, let us say 1 or 2, okay, in the conduction band, and similarly in the n side you have 1 or 2 holes in the valence band. Okay. So, now you can think of the currents. Okay. So, this is the space charge region, right, where the band bends. So, this is the space charge region where the field is not equal to 0, is not it, but rest of the thing, even if you have a distribution of different charge carriers, it is quasi neutral region, this we discussed. Okay. So, think of the life of this particular electron. Okay. Let us say this particular electron we are looking at, we are sitting on that electron. Now, due to thermal random motion, it will go here and there, and as long as it is in the quasi neutral region, it will not effectively go in any direction. But such a wandering electron, if it comes to this position where field is not equal to 0 at the edge, it will be sucked in. So, this particular electron will be sucked in to the other direction, because you have a downhill direction in the energy. So, it will just go in the other direction inside. Okay. So, what we can write that electrons in the edge of space charge region will go downhill from p side to n side, and that is what, that motion is happening due to the field, right. Xi is not equal to 0, that means it is going in the direction of field, or the electron is going against the field. So, the effectively what we are having is an effective electron drift motion, and that will give you a drift current, and of course, whichever direction electron goes, the current direction is opposite. So, what you can write, J n drift due to this itinerant electron which was moving around, and as soon as it comes at the edge of the space charge region, it is sucked into the other direction, in the other side, n side. Okay. And similarly, if you think of the life of this, the minority holes, again whenever it is coming towards the edge, it will be sucked in the other direction. Even if it looks, it is not going downhill, it is going as if uphill, but for holes we have seen that the energy is going up downward direction. So, again this is downhill for the hole. Okay. So, we will have and drift, hole drift from the N side to the P side, and effectively we will have a drift current. And now whichever direction the hole moves, the current is in the same direction. So, what we can write, this will be Jp drift, and this drift is only for the minority carriers. In the N side it is hole, which is the minority carrier, and they are getting drifted due to this downhill energy in the space charge region, right. And for the electrons, the downhill direction is for the minority electrons only, which are coming from the P side to the N side. Okay. Now, look at the other thing, which is the diffusion current. Okay. So, in the N side, if you see that electron concentration is much higher than the P side, right. So, you have a concentration gradient across the space charge region from N side to the P side for the electrons. Okay. So, as concentration is higher, there will be a diffusion current towards the P side. So, you can write that there will be a diffusion current, diffusion flux for electrons, right. Now, all these all these electrons which are like gathered at the edge of space charge region in the N side, all of them will not be able to cross the uphill region. So, for this electron, these electrons, it is uphill, right. So, not all of them will be able to go, few of them will, there will be random motion, few of them will come back because it cannot cross the energy barrier, and some of them will go to the other direction. And this diffusion flux will of course depend on the energy barrier. Okay. So, let me write here the diffusion flux will depend on the energy barrier. Why? Because that will tell how many of them will be able to cross it and how many of them will not be able to cross it. Okay. So, again if you look at the diffusion current density, that will be J n diffusion, again that will be in the opposite direction of the electron motion. Okay. So, for the electron you have this diffusion current density and this drift current density. Okay. And similarly, the same thing will happen for the holes. So, let me use this particular symbol or color, that holes again it will, some of them will try and come back and some of them will be able to go in the other direction. Okay. So, if I use a dotted line here, okay, some of them will go, and what you have is this Jp, not Jp, but hole flux towards N side. Okay. And the majority carriers are going through this diffusive process and minority carriers are going through the drift process. Okay. So, the effective value or effective contribution to the charge density or electron, the current density will be Jp diffusion, right. So, please pay attention to this particular phenomena, what is happening, how the diffusion and drift is happening, and which carriers are participating in what way. Okay. If you need, you please go back to this portion of the video again and try to assimilate the concept. So, what we can write here, few observations, that majority carriers in either side take part in diffusion current or diffusion process, right, not the minority carriers. And the diffusion process, it depends on the energy barrier, okay, or the height of the hill that it has to cross, which is the height of the hill. Okay. And on the other hand, the minority carrier, I should say is minority carriers in either side take part in drift process. Drift process means what? It depends on the field. Okay. So, drift process, whenever an itinerant electron or hole comes near the space charge region edge, it is sucked into the other side. So, that is drift, but that does not depend on what is the height of the hill. In downhill, you do not care how deep it is. When you are coming down, you can take a stair, okay? You do not have to go through a lift, but when you are going up, it is difficult to climb the stairs. You can take a lift, or you should take a lift if you want to save energy. So, these electrons and holes, they are also lazy, okay, in metaphorical sense of course, and they do not care when they are going downhill, they do not care about how deep it is. So, this drift does not depend on the value of the energy barrier. It is only the diffusion current that depends on the value of the energy barrier. Okay. Now, still we have talked about equilibrium, okay, and that is why we have kept the Fermi level constant Okay. So, under equilibrium we do not have any effective current, right. So, no effective current. So, whatever is happening with this drift and diffusion, they have to balance each other under equilibrium, is not it. So, drift and diffusion have to balance each other, and not only the overall current density has to be matched, it has to be matched in either conduction band or in valence band, right. So, electron, there should be no effective transfer of electron from any side, okay, and similarly for the holes. So, individually there has to be equilibrium both in conduction band and in valence band. So, what you can write, that for the conduction band this J n diffusion is nothing but J n drift, then only if they have the same magnitude and they are opposing each other. So, basically there will be equilibrium or no effective transfer, and similarly for the valence band you have this equality of magnitude for the whole current, diffusion current and drift current, and again you will see that they are in opposite direction. So, here you see here that the diffusion and JP drift, they are in opposite direction. So, they have to match each other in magnitude, and here also for Jn diffusion is opposing the Jn drift. So, again their magnitude has to be equal. Okay. So, this is individual equilibrium in conduction band and in valence band is necessary, right, and their equality is giving you the equilibrium condition, that no effective transfer of charge. Now, what will happen to the concentration profile? Okay. So, under equilibrium there will be no charge transfer. So, whatever is drifting to the, for electrons, whatever is drifting to the n side, it has to be matched with the whatever is diffusing to the p side. So, basically no charge transfer, no change in concentration in either side of the junction, okay, for either kind of charge carrier. So, both electrons and holes, they will be, the concentrations will be maintained at the same level all the time. Okay. Now, if we want to look at how this will change. Okay. So, let us say that this is the carrier concentration in this direction. It can be electron or hole, and this is the distance. So, let us say the space charge region is here. Let me use another color. Okay, space charge region is here. So, what you can write that, and this is the p side and this is the n side. Okay. Yeah. Now, in the p side you can say that the majority carrier will be holes. Okay. So, we have a large value here which is p naught. So, under equilibrium, what is the hole concentration in the p side, and similarly in the n side it will be a much less value of holes. So, we can write it p n naught, right. So, and now for the electrons it will be majority carrier in the n side. So, it will has to have some value greater than the minority carrier. So, let us say this is the value in the n side, the electron concentration value under equilibrium. Okay. And on the other hand, in the p side electron will be minority carrier, it will have less amount. So, this is n p naught, right, and in between there has to be continuity in the space charge region. So, the whole concentration should come down like this and the electron concentration should go up like this, right. So, that will, the under equilibrium, that will typically the scenario of concentration in two sides. And now you also know how to quantify them, right. So, P naught, you have seen that it is dependent on the acceptor dopant concentration, and for the N side the majority carrier depends on the donor dopant concentration ND. Okay. And the ratio of the majority and minority carrier, that we obtained from the equation of, so this Np naught will be equal to Ni square divided by Na. Okay. Acceptor dopant concentration is only relevant in P side. Okay. So, that will depend on Ni squared by Na, and here in the N side the minority carrier concentration will depend on Ni squared by Nd. Okay. So, you will get this information that I am writing in the plot from these relationships. Okay. So, that is how we are getting these concentrations. So, here you note that in the N side this difference in majority and minority carrier concentrations depend on Nd, or the donor dopant concentration, and on the other hand in the P side the same thing, that means the difference in majority and minority carrier concentrations depends on Na. Okay. Because that is the P side and acceptor dopant concentration is what determining the majority and minority carrier ratio. Okay. So, that is how this junction PN junction is working internally under equilibrium, what are the concentrations and how the electrons and holes will diffuse and drift and balance each other, that we have seen today. So, in the next class what we are going to look at is the non-equilibrium condition. If you apply some voltage, if you apply some potential, how this whole thing changes, that is what we are going to look at in the next class. Thank you for your attention.